Let us see how we can use from the knowledge we have already learned in Reed-Solomon codes, that this idea can be applied to reduce bandwidth in case of storage. And this was actually attempted practically. I mean, most of some of the results, in fact most of the well-known reconstruction codes came from industry, and the technology, the theory used is not very big. But on the other hand, if you want to understand the limits, what is maximum possible in this, it requires much other deeper theory which may not be able to kind of cover today, but I would like to bring in those issues here. Then we will actually discuss the issues through some examples of LRC codes used in Windows, Azure and Sorbas. In fact, Hadoop we are currently doing, and so maybe some of the ideas will become much more clearer when we demonstrate how Hadoop works and how, for example, a programming paradigm in Hadoop uses the storage. Okay, so that's what we do. So basically, this is the main idea about the locality that came through an interesting paper by Gopal and Huang and Simiti and Yakonin, and this published in 2012. This actually main application is basically distributed storage that require code designs that minimize the number of surviving nodes access to repair a node. So in the first introduction itself, we did mention that storage codes were there, and if you want to actually keep the data efficiently, MDS codes are the best way to go. So they, for a given reliability requirement, that is, it gives an optimum storage, what you do. Only problem with the MDS code was that when a node is failed, then repairing would require downloading k other symbols, and depending on how the data bytes are arranged based on the code, which you all probably have an understanding now that every symbol in a Reed-Solomon code is actually a file, say a block or a fragment. So if there is a nk Reed-Solomon code, what we do is that if whatever may be the file, they are divided into k fragments, and out of these k fragments there are n minus k fragments are created, and these things are stored in different nodes. So essentially in a system, in a distributed system, so when the program needs a certain data, it throws, okay, I need that, I need to read the data, and obviously there will be some, just like the thing that Aaron mentioned yesterday, so there will be a made out call out for reading, and automatically there are many parallel things coming. So obviously accessing the data from a node is an important measure of important resource that is required to repair a node. So minimizing that, so these two ideas that came up in the beginning of the course, I said, is the local regenerative codes and codes with locality. These two actually approach the same problem from a slightly different viewpoint. In the local regenerative code, the focus is actually repairing bandwidth. So obviously, when you need k different nodes to be there, so you need to actually minimize the bandwidth, and we looked at the bandwidth and storage trade-off, and that led to a lot of big theory, and whole lots of activities are happening. On the other hand, when you design a storage system through a practical system like either a Windows, Azure or Hadoop or something, then what we need is basically whenever a data is required a particular node, it actually calls a read. So if the number of devices that a particular process needs to get for data, if that is minimized, obviously automatically bandwidth is minimized, right? So second approach is basically the regenerative code focus on repair bandwidth. The codes with locality, on the other hand, address related issue of reducing data reads and also data access. So really handling too many nodes, handling that itself adds to the cost, and you want to minimize that. So in terms of in terms of code, you can also something like a degree here. So for example, a particular node has to connect to certain in a graph point of view, so to connects to some other nodes to repair this. Then if the connections are represented as a graph and you see the degree. So what codes with locality will do is to actually reduce the degree of that association in the graph. So obviously this was done with a practical focus, and so NKD code is said to have a locality R if any symbol can be recovered by accessing at most R other code symbols. So if you have a code symbol written there, now you look at the structure of the code. I will come back to some definitions and then trying to actually at least tell you about the important problems in the area, but there are other things. So the papers 2 and 3 at the end, one is this one, the other one is from the Windows Azure, present the Sorbos actually, the present studies and the implementation and performance of such codes with locality. So some of these two papers actually comes up with more practical flavor and tells you actually opting these codes, you actually gain something. In fact, Windows Azure people, the Microsoft Windows has saved so many thousands of dollars actually in this. Remember what's happening if you want to keep certain file data in storage, and for the storage what you need is just the hardware. First of all, hardware needs to be there, then it's not the hardware, and then after that you need cooling and the energy to maintain that. So obviously lesser the better, and so reducing this would help. So we will see the detail of code design, how it happens in the things. So just to kind of understand a bit more on the issues pertaining to this here. So consider now NK. So the problem with the notations in this area, they've used some of these words that we use for other purposes. For example, sometimes we use R for rate, and here the small r is used, and sometimes even K it is used in a bit different way here, and also so obviously some of these terminologies when you are understanding B, focus on the local one. I'll be switching between the things pretty easily. For example, the first two slides will be a little bit different than the other things. So let's consider now NK. Now again, I didn't put D here because the problem is in regenerative code thing is D is used as a repair degree. That means the number of nodes that a particular node needs to contact, and the D obviously in our RS coding you use the D min. So let's say we'll take delta, so NK delta code. So you have every code word now can be represented as C0 to Cn-1, where Ci are code symbols. Ci's all these are code symbols. So definition is the ith coordinate of C has a so now each coordinate has a locality R if the value at the coordinate can be recovered from accessing R other coordinates of the code. So we call a code C a linear R delta code of minimum distance delta if all the information symbols have a locality at most R. So here in the thing is R is a locality. So then you see you can ask this question, for example, if ith coordinate say C0 to to repair C0, what might happen is, so let us say Cn-1, say for example C0, this one, another one. So some of these group of R symbols, they themselves form say R length code, and that can be R delta with the minimum distance. So for example, that is the delta here in this case is for the minimum distance of the whole code. They have information locality means maybe out of this there are some are information bits and some are parity bits. So this initial definition is thrown only for the information symbols. So in R delta, R code with R delta with the minimum distance delta is R locality R if all the information symbols have r other coordinates, at most r, sometimes can be less than that, that form a code in itself, and so using that you can recover the code. Now and that's also, you can see that this definition, and sometimes there is also another type of class you can think where you want r locality for every symbol in the code. That means even if parity symbol is deleted, then you can connect some other, at most r number of other symbols. Not necessarily, for example, for this one there could be one other r1, for this one another r set, no problems, there is no restriction that, but you can always group them. For example, if these and these are within the same r set, they are all in the same group, so they all can be recovered by contacting other ones. This is the kind of definition, and you would like to have some bounds on it. Now what the person, the Gopalan and other people, they showed was, basically if you have such a constraint, so then they try to put a lower bound on. So now remember, Reed-Solomon codes are optimal, not much you can do, and the minimum distance they give is also optimum. So that means that they follow they actually satisfy the singleton bound with equality. Now what if you are interested in actually creating this one, and so this particular n minus k, so linear code with information locality r, then n minus k has to be greater than or equal to k divided by r, and it is a floor function plus d min minus 2. Pardon? It is a ceiling, that is what I said, sorry, not floor, ceiling function. So this is the smallest integer greater than or equal to this number, ceiling. Yeah. So in this one you can see that, so for example when locality happen to be r, sorry, like equal to k itself, which is the case of Reed-Solomon code, then what happens here, you apply k equal to r, then this becomes 1, then it is the d min, this plus 1 will be d min minus 1, so the d min is now greater than or equal to n minus k plus 1. That actually tells you it's a singleton bound. So that means that the Reed-Solomon codes actually, this is a generalization of a Reed-Solomon code, this generalizes singleton bound, but because now you insist that some of the other symbols should have a locality r, then you start paying some penalty, and so obviously just you want a little more r, then the penalty starts increasing, so you can't achieve both. So you can't get the locality and as well as having the singleton bound minimum distance. So that means that forcing the locality actually on an MDS code, certain minimum thing that you need to tolerate, minimum degradation in the distance. Okay. So is that idea clear? At least this portion. These are all the code symbols. So this is the first symbol, the second symbol, and Cn minus 1. So obviously if you want a different code word, you need to have another index which I have not indicated here. Yeah, is that clear now? So the question was, basically obviously a code is a collection of code words, so the indices, it should be for all the code words. So what I want to highlight is that if you take a code word and put them in a matrix, right, so you have obviously all the rows will give you different columns, but I don't care about that. I am only thinking about taking care of the symbols. So the first symbol, second symbol
in a specific code word,
and every code word the first symbol, and every code word second symbol, and so forth. So if I am able to for example recover, so for example if one symbol is gone, recovered means
in a code word.
In a code word.
Okay.
So you need,
I can repair it with some certain symbols in same code word.
yes.
Okay.
Yeah. So I think I will probably, this is the reason I think perhaps it would be better to actually illustrate a Hadoop system understanding that. So what's happening is you can assume that you have different storage nodes. So in this case let us say this is a 0th 1 2 up to n minus 1 length of the code. So each symbol now represents a node. So each symbol can be a byte or a word or a something, it's a node. So but when for example a particular program or particular node requested data from a particular fragment, so you will actually get all the symbols associated, because obviously let us say the data is now set as a block in these code words. It's a long strip of strips. So when something is downloaded, so the first symbol of, let us say, of L of them, they actually form a code word in the code. This is how RS coding is used. So maybe it will become much more clearer when we show some implementation. So you can see that. So each node, so now each one is a symbol. Okay. So this is what I meant here. Each one is a symbol. And so obviously if a particular node has failed, means that you need to repair. So in case of Reed-Solomon code, I need to contact at least k other nodes to recover it. Okay. And let's say if I am interested in this fragment, I need k other fragments, and it sometimes comes in Hadoop as a blocks. In some other, in some other, in Windows system, it may be called as fragments and so forth. But it, it varies from how, from one programming paradigm to the other. So as far as we all understand, it's a block. So what happens is that now the program has to go through each one of them and then recover. Yeah. So that's a kind of a, so but now advantage of the locality. So for example with Reed-Solomon code, I need to actually contact k of them. Now I only contact with with RS coding. Now repair requires access to k nodes, k surviving nodes, whereas the concept here with locality, we now reduce it to R nodes. Okay. I might change over the notation depending on when I discuss the Azure or something. Okay, that's because those authors use the different one. I don't want to unify the terminology for all this one at this point. But the ideas is important. So in such case, if you go and look for a general now everything is clear. So NK linear code. So now this idea of locality doesn't need to be only to MDS code. This idea these people have generalized, and so this paper talks about a general linear code. And if you now insist that your code should have a locality R, then n minus k has to be greater than or equal to this. And now you can see that this, really what they show is that they look at possibilities of all these codes and greedily start taking vectors of q minus 1, and then this is a kind of some of the properties of parity check matrix that introduced during the bounds. Similar kind of things will be used, but then in conjunction with some other graph theoretic problems, then you show that the d minimum has to be greater than or equal to the same type of argument. And so what the property that is used in this paper is that you consider an MDS code, and then look at the generator matrix of this code, and any k of them you look at the rank of that submatrix is always be non-singular. And so what they try to do is, without using general thing, they'll start constructing this code, and they always show that by insisting this R thing, they will be able to achieve this bound. They show the lower bound, it has to be greater than or equal to that, and then of course constructing a codes meeting this bound will be a challenge, and that will be research that they do, and there are so many papers have been there on that. Yeah. So the idea is that the requirement, you can say that n minus k, because of that there is a something. So that one thing is clear, that if I want now a locality less than k with Reed-Solomon code, I had to have some penalty. So I should be ready for that. So this means that people are a little bit relaxed now. So I can't get like RS code, so whatever solution you get should be better. So this is what they do, and I look at now Microsoft Azure LRC. This is a very interesting code, and a little bit of background on, I mean, this is actually the real system being used, and it's bringing benefits of worth thousands of $1 million to Microsoft company in terms of the storage efficiency and etc. I will explain how this happens. So probably the context of this explanation will become much more clearer as we go through when we demonstrate Hadoop, how it performs. Similar to that, the Microsoft system also performs, and what they have called as some kind of whenever a file become hot, that means that is being created. And they have a policy, because remember Microsoft, people could generate some data and say, okay, please share this, and they may send it to someone. So an application would be, you created data and you want to send it to someone, and it's just the purpose is only to transfer them, okay, but you don't want to send it through email. So you will say something to the whatever their supported email, then what they do is they make that thing available to the other users. So now whenever a new file is created, so this is something called a stream model, and some of the things that Aaron will talk at the end might be somewhat related to that area. I am not fully sure, but we'll see that. With the stream model, the model is that you have a file, and the only policy is that you append it. So for example, anything happens to that file, you keep on appending to that, and as it becomes 1 gigabit or 1 gigabyte, then it's been, after that no more things will be done. Then that's the time it's no more hard, then it will get writed, and it will get writed and stored. And so like that the data can generate like this. So when it is hot, it gets used, and it's always append policy. So the now you want to actually handle such fragments, and I want to efficiently store it. Okay, so when it is completely active, it's hot, just as in Hadoop, this data also will be replicated. So really the initial days when the data is really hot, it will be available in multiple nodes, and it becomes easier for the cloud system to make the data available to the processors as and when required. All the things that we mentioned in the other talk, that will happen. Okay, is that clear? Some kind of a general thing. But once it's almost let us say reach the limit and it needs ready for writing, at that time the fragments are started and writing. It just stopped, and it uses something like an RS code. But I'll just explain about the coding things. What it does is that from 6 data blocks, it generates 4 parity blocks. Just like then it will become 10. So additional will be, there will be 4 additional blocks. So for example, each one is now a byte. For every 6 bytes, there will be 4 more bytes of parity. Now you actually divide these parities into 2 parts. So for example, there is one P0 and P1, which is a global parity that depends on all of these 6 symbols. Okay, so all P0, P1 is a global parity. They are computed as a function of all 6 data blocks. Then what it does is then it actually computes other 2 parities, which these are all, here what you do is that the data blocks are divided into 2 equal size subgroups, and the local parity is computed for each group. So what you do is basically, I have 6 blocks now, I am going to group it, these 2, and create two local parities for it, and local parity is simply sum of them. So extracting that, it's a simple RS code, it's a trivial RS code, so it can one node failure can be easily recovered. So you see the first local parity is, they call it as Px, and the second one for the first 3 blocks, and second parity is called as Py. So this works exactly like this. So now you have a 6 data symbols divided into 3 parts, x0, x1, x2, and you create a local parity, y0, y1, y2, another local parity, and so now you have a global parity. So now such class of codes, that is a general class where if you have k symbols and you can divide into certain size L, which I will come back to that in a general mode, and each of them have a local parity, and after that some two global parities, they are just like another Reed-Solomon code that depends on everything. So in fact this P0 and P1 will be depending on all of them, these will be depending these three things. So obviously remember these nodes will be in the different, it can be in the different part in the cold storage. No, there is no, they can be in the cluster like the one which Aaron told you. So they can be in different places. So the code is very simple. So which RS code this, in terms of the storage, what is the equivalent RS code you can think of? 10.6 code. Okay, n is 10 and this is 6. So for repairing the failure of any node one data block, it requires now. So obviously if the the primary this survives only the first 3 surviving blocks. So you look at the where is the failed node group belongs to. You contact the other 2 other 3 nodes in the group, because it's 3 plus 1 4. So other 3 nodes in the group, and you can easily do it. So obviously now you can repair it. So if it is in RS code, you had to contact 6. Now suddenly 3. So it's almost 50% improvement. So LRC has 4 parity blocks in total, and it can tolerate up to 4. In fact, the toleration to different type of errors can be different in this, because it's not completely MDS, because so that's why LRC has only in total, and it can tolerate up to 4 node failures, but not all 4 node failures. So that's because it is not an MDS, and hence cannot tolerate arbitrary. So if there are arbitrary 4 nodes failures, then it is not possible. So now let's look at the definition. So this way here I use a little bit different notation. So K is still same. That's K and L comma R, LRC local reconstruction code, divides K data fragments into L groups with K by L data fragments in each group. So whatever may be the K, you divide it, and for purpose of without loss, because you don't take it into a fraction one, you always take something L which divides divides integer. So it computes 1 local parity for each group. In addition, it computes in a small r global parity. So now R is a word reserved, in this case is a different way in the previous formulation there. So but this is the one. You see, so it computes R global parities from all other data. So the total length of the code is same as K plus L plus R. Is that clear? Because there for every K, there are L parities or local parities are added, and it's R. So you can say that the storage overhead in this case is n divided by K. So n is this, and divided by K is 1 plus L plus R by K. So you can see that L plus R by K is the excess that we use for the penalty that we pay for the local thing. So you can see that if 622 discussed as a storage overhead of 1.67x. So the code definition also needs to have details of coding equations that determine how parities are computed in each problem. So sometimes you can choose that LRCs can achieve maximal recoverable property. So you can easily see that it is not there are many codes that is not detectable. So that I will come back to that. So the LRCs can achieve maximal recoverable property. So what happens is that LRCs cannot recover some other things, but they are already that has a maximal recoverable property. It means that LRC can decode any failure pattern which is information theoretically possible. Now when they use information theoretically possible, there is a formulation is a bit more different, and I will not go much into details into this in this lecture. So for example, here you take the same issue happens. So here in this particular example you have so where here here, so here R is 2.
If x1 fails, How many nodes to be accessed? 3.
So L is 2 here. So see in this particular
Nodes to be accessed by node fields.
now that see you will access k divided by L number of things, you know, each. So you know this will be k divided by L is each group. So if a node fails, you need to access k divided by L other nodes to repair it. 3 nodes to repair it, and 3 is basically 6 divided by 2, correct? So this is L, this is R.
So R is not the number of nodes to be accessed.
No. Yeah, R is the in this particular formulation. R is the global parity. R is global parity. L is the parameter for the local. So L tells you how many different repair groups are there, local groups are there, and so k divided by L tells you the minimum number of nodes you need to contact a repaired node in a group. Of course, if there are more than error thing can happen in the group, that we have to see. So that's what I was going to consider here. So this is what this is clear 4 by 6 this question. So now the code definition also needs to have details of coding equations that determine how parities are computed. Let's see what is maximally recoverable property. So for example, first we have to see that non-recoverable cases. So you can say that you know the code now you can represent it as x0, x1, x2, and it is px, y0, y1, y2, py, and p0, p1. This is a global parity. This is how the LS local parity, global parity will look at, and all these are all related. Okay, that's how it is there. So for example, the failure pattern, say if you have x0, x1, x2, all of this group, and this group is completely gone, whole local group is gone, then that is not decodable, because there is no way there is not enough information you know with these parities. So you only, so once this is gone, you only get 2 different unknowns, but there are 4 different unknowns to be recovered, so you can never recover it. Okay, so obviously, but such things, such failures sometimes are actually non-decodable anyway, because now our the constraint that we have imposed on local reconstruction is that the code locally it should be able to reconstruct. This actually this puts that constraint, and so obviously if you remove the whole local group, there is not enough global equation to recover it, and so it's information theoretically it is impossible to decodable. For example, the failure pattern x0, x1, y0, y1 is decodable. Let's see how that is possible. So you have, let us say, x0, so x0 is gone, and x0, x1, and y0, y1 is you know all these things. How in what way you can decode? So first of all, there will be one local equations about this you get, another location you get here, and there are 2 global equations. These of course you have to construct in, so the construction of a local reconstruction code is that when this is possible here, the code should be such that you know that becomes non-singular with these 4 unknowns, and you should be able to decode it. So when you are constructing it, you put these constraints and start looking for solution. So the solution can differ from g of 2 power 4 is another solution. If you use the field to be g of 2 power 8, another solution, and so forth. Okay, is that clear? This is how this works through. So this is the failure patterns. So such failure patterns are to be information theoretically non-decodable. So failure patterns that are possible to reconstruct are called, you know, they are information theoretically decodable, and for example, this is one of the things. So in fact, for any nk linear code to have this property, so now what is happening, we will put if you now asking for these requirements, now we can formulate the problems like for nk linear code to have the property, arbitrary r plus 1 symbols must be decoded. Okay. So, you should be able to decode any r plus 1 symbol, that's possible, because there are r global equations, you can say, and tolerate more than r plus 1 errors, provided the errors are information theoretically decodable. So, if it is possible to decode information theoretically, you should be able to decode. Okay. Now, single data symbol failure can be recovered from k divided by L symbols, and the following condition is definitely is requirement. So, n minus k is L times r. So, LRC achieves these properties with minimal number of parities. So, if you have all these questions, LRC now achieve this with minimum proper parities. Now, what do I mean, for example, what are the complexities involved? So, you can
what is this R here in MK linear when we are talking of general linear codes?
Yeah. So, here L is the number of repair groups, same as this is LRCs only.
So, initially you wrote for any NK linear code.
This is for any NK linear code, yeah.
So, any NK linear code is, you are talking of LRC.
Yeah, I can say I'm decodable, I mean you can limit it to MDS code, but this definition takes care of actually decoding for any linear code.
So it's basically
K, so not K and R. So KLR, okay, yes, exactly, K, L and R. So LR is actually denotes the additional parities that you add. So there will be K by L local symbols, parity symbols, and R general global symbols. So now what you do is that, so because of these R plus 1 symbols, so let us say that could be any other positions, and you can on our RS code, let us say we impose this on RS code, then you can use that van der Monde construction and say in all those positions my matrix should be non-zero, because I need to recover R plus 1 errors, global one, and obviously locality achieving is easy. So now you put the local constraints, so that will starts reducing the number of equations possible. So the more instruction, more details are there in that paper that we mentioned. So you probably, if you go through that, and we will come back on that. So LRC achieve these properties with the minimum number of parities. So a little bit of let's do the discussion on this code, how for example this achieves better performance than RS code. So here so now you can see that when you are looking at the graph here, so because of what it does is that you can consider the storage overhead and the basically reconstruction cost. So what's the reconstruction cost in our case here? Say this is reconstruction cost and the storage overhead. So obviously if you say use let us say RS code of let us say 6.3 RS code, that's been a popular code used. So RS code 6,3, that means k equal to 3 and n equal to 3. What is the storage overhead? 50% of the overhead, yeah. And but in general you can ask actually the reconstruction cost and the storage overhead. You would if you actually have more storage, then reconstruction cost will be smaller, yeah. And if you have less storage, you have to have a reconstruction cost more. So in general, any reconstruction cost over or the overhead, you will have something the same type of a inequality trade-off that we mentioned. So as you can see that when the storage overhead is less, you have to have a more work to get the things done. And so what people can do is that they can look at use a particular code, throw it into the system and make some measurements and actually point. So you will get different points, feasible points. So anything above, and there may be also some kind of limit that comes from these issues in distributed systems, and this code almost looks like that. So this is what you could actually practically you can determine. So if you normally in a storage case, Reed-Solomon codes are used, and for example with RS-63 code, which has about 50% overhead in storage, but this actually the cost for reconstruction is it has to collect 6 different nodes. So that will be the cost, but its storage is half. Now what we can do is that we can actually find the corresponding LRCs that achieve, pardon? Oh yeah, no, 6.3 code. So the length is n. Oh, okay, sorry. This should be 3. Yeah. So here the storage is. See, I just noted down today morning. Let us say. So this is the storage overhead. So let's say you will take the LRC code here of this is LRC 12, 4 and 2. So what's the storage overhead is for this also? 2. Now this is 2. So this is a 6K code. So the storage overhead is 1.5x. But you could so you will let me check. So this is 6.3 code, and the another code that actually achieves better this is let us say lower storage than that is 12, 2, 2. So n length is n 2, 2. What is the storage for this? Is actually this is 50%. This will be 1.33. So 1.33, this is 1.5 because of the size, right? 1.5x, this is also 1.33x. You can see that 6.3 is 50, right? You are adding 50% more. Here it is 6, 12, you are only adding 4. So it's 1/3 more only. So here, but here to repair here, in fact, the cost of these is both are same because you contact 6 nodes. For example, here, so here, how many nodes will be there in each group? 4. So so let me let's just think through this, and I just wrote down before coming here. So here, so let's look at this code now.
RS-63 should have a storage overhead of 2.
Storage overhead of that's 1.5x. Okay.
So it should be n by k.
No, yeah, that's so you need 50% more. So for example, for every k, you add one other k. Yeah. So whereas here, for every totally 12. For 12 information, you only add 50% more. It's the same code in terms of. Pardon?
By the definition, it goes like n by k, right?
No, so n by see k divided by n. You are saying the rate? Huh? Pardon?
You mentioned overhead as n by k.
Okay, so you can say that overhead is always. So what I'm saying is that always you have the additional information, k times how many. So overhead has to depend on. So if you have a k information bit, k information symbols plus additional symbols, how much you add? It is n minus k, which is 3 here, right? So 3. So as a function of it all depends on. So this is actually, you can say that for every information symbol, you add half of them as parities, So for every 6 information bit, so this is actually say k. Sorry, I think that's the confusion. So RS code, it's k is the number of parities you add, right? Okay, I probably you are all confused. All the confusion is because that we of the nomenclature. So let me check the definition of LRC. We use
Why it is n by k? N is the total number of symbols.
Okay. Overhead is n. So here you see the LRC discusses the overhead of. So here you have a 4 by additional symbols. Okay. So when you define here, I have defined LRC defines k is the first one. So you have to actually come up with, so remember the confusion is because when we referring to RS codes, we are referring it as RS of n comma k code. Whereas when I am now talking here, LRC always starts with k, that is the k is the information bit, and L divides you the number of groups, and R divides you the additional symbols. So total length for the code is k plus L plus R. So here the total length for the code here is 9 and k. This is if you want to say n k, it is that of that type. Okay. So do you see the point?
No, in RS 6 itself is the total length.
No, that's what I am saying is, so when I am now making, let's worry about it. We will only we have these 2 points here, 12, 4, 2 code. Okay, so let's say this is k, this is L, and this is R. So what's the length of this code? 18 and k is 12. Okay, so obviously what is the k by, you can say that k by it's almost no, it's 6, right? K is this, and additional parities that you use is 4 plus 2 6. So k is 12 plus 6 is 18. Okay, 18. Okay.
That way also we are getting 1.5. So n by k, 18 by.
Yes, so 1.5x, correct. That's the additional storage required. Now what is additional storage required for this one? 12 plus 4, 1.33, right? So, but this code, I mean, what I am saying is that there is a code which is which works as 6.3 Reed-Solomon code, which has here is 12 divided by 2, 6. So this is basically k is 6 and 3. So it is 9, 6 Reed-Solomon code, NK code. Okay. Now what's the overhead here? Again 50%. So it's 1.5. Correct. So but to repair any of this you need contact 6 node words. Whereas with this 112 code now, so for the same storage requirement, so this LRC only contacts 3, which is basically half of this one. Is that clear? So I think the problem was when I wrote initially RS code, I wrote k and the number of parities, right? So that's a different notation compared to this. Is the problem with this thing. So here, but I now reformulated here. This correct code is n equal to 9 and k equal to 6 code. What's the storage overhead here? 1.5 is the same as this, but in order to repair it, you need to contact k equal to 6 different nodes, whereas in this LRC code you only contact k equal to 12 divided by 4, which is 3, which is no 12 divided by 4, which is 3, yeah, which is half of k, which is 6. So really you get a 50% improvement over the bandwidth. On the other hand, you look at, if you want to keep the same reconstruction cost, then I can take 12 12 2 code. This has a reconstruction cost of 6, but its storage is 1.3. So, in either case, whether you fix the reconstruction cost, I get a LRC code which has a much lower storage overhead, and whereas if you keep the main storage overhead, then the LRC code will have a better reconstruction property. So, here the reconstruction directly refers to the number of bytes downloaded to repair it. So, the moment you contact less number of nodes, you gain. So, this is the kind of advantage you can see, and in fact in general industry circle, this is also what I want to talk about a bit more on it. For example, here reconstruction cost and storage overhead, reconstruction cost is proportional to bandwidth, storage overhead is proportional to the storage what we have. So, this has similarities to the storage and bandwidth trade off that we considered in the LRC. So, under this also you get a similar idea, and in practice depending on how efficiently you implement these distributed system storage systems, you could actually compute this, and many practical papers using these codes will try to identify their point in it. For example, this may be all the solutions may be here, and so let us say under some requirements you are better than the here like that, but you can never go beyond that, because there is that's the kind of trade off that we. So, this is in some sense it actually informs us actually how to design good codes for this, and so for example these people actually did it, and in their papers they describe how they can do it for GF2 square or GF2 power 4, which is small enough. That indicates that this idea, that is the reconstruction, can be achieved with a small finite field, whereas with the network coding results that we mentioned 2 days ago, with using functional repair, the solution exists only if the finite field is quite big enough, very large finite field. And of course, there are some improvements taking place in that place, but here by just playing around with the codes that are already there in literature, you could come up with technology, and this has been really used, and this actually matches to the their idea of stream processing, in some sense that any particular file as there, a stream of file could be allocated in a particular memory, and when you start developing it, any object you create, the things could be appended. How that particular file object is used in say for example in distributed system is not our concern, okay, but you could there are lots of improvements happening in how to handle the distributed storage itself in distributed storage community. So if it's possible, if you could keep these two design spaces separate, that will be nice, right? And so LRC is actually in that way matches to that kind of a industry need, and what they want is a property in storage is scalability. That means whatever you try to do with a small size, should be available for even if the files becoming big, and this gives a flexible method. And so I also described actually how far you could do. So in fact they do have some more theoretical results in identifying these ones, theoretical results showing that their design meets with the information theoretical principle. That's a lower bound, can't do better than that. And now we know at least, okay, if I need to add some extra local parities, and that is acceptable. So in our practical work in informing from this, we also took a similar type of ad hoc decision. So when we design our storage clusters, and in our case our storage clusters are geographically distributed, and we know from the very beginning they are geographically distributed, and sometimes some problems require us our nodes to be geographically distributed for resiliency, other properties, and there may be some other requirements. User may put all my files, and at least some files should be there in one location, it can't leave this country, for example. In such cases we tend to take a view that maybe adding some additional property and gain the efficiency in accessing the node. So, the Sorbos is another such LRC was done. So, this was I am telling you the developments happening in Microsoft research. Now, here in the Sorbos LRC, that is this is actually work presented by Satya Murthy and other group of people, where they actually improved our traditional erasure codes that allows to recover 2 errors efficiently. So, they basically worked with the Facebook's RS code. So, in these people Windows, they had 6.3 they were using, which is that is 9.6 code, and they were using RS codes, and they tried to improve on these, whereas the Sorbos actually comes up with Facebook development, which were using 1410 Reed-Solomon code. The technique behind the new code is actually the expansion of the MDS code, namely Reed-Solomon, with 3 parities. Okay. So, each parity corresponds to XOR of certain amounts of data blocks, the last one being the XOR of the MDS code parity. So, what they did was basically they took out the 2 extra parities of the RS code and made it like a local. So, I will explain this one like as follows. So, this is the canonical example. So, for example, first 5 nodes. So, because RS code that is used in Sorbos was 14. So, here you see the notation for the code comes back to NK code. So, some group who works on that one, they keep the traditional RS1, and the local regenerative group, when they are working on, they invented their own one, and they think that this is a better way, and they keep sticking into that. Now, when we try to do some, we will get into this trouble. So, you need to make first of all these translations, otherwise it does not make sense. Yeah? I thought this probably was interesting, it went well. So, let us take here. So, there are parities. What they did was this 4 parities are there. So, they did not want to affect that, they wanted to keep the existing things because it is not good to change over. They add 2 more parities, S1 and S2. These 2 parities basically increase the redundancy a little bit more. So, you will spend a little bit more storage, but then you get some resiliency. For example, if one node is failed, now I only contact within the group to recover it, because I added XOR. Okay. And of course, if you add it to the parities as well, then you will get the all symbol locality as well. Okay. But this sometimes in some application they do not use, or this is an option. So, it is possible to kind of appreciate that the most common scenario is 1 erasure, and that can be quickly recovered from local parity. That is what that thing did. So, recovery is very easy. So, in case of 2 errors, if they happen to be 1 on each partition, then the repair process is performed efficiently. But nevertheless, in any case, local repair process will fail, and the normal. So, if for example, if more than 1 error happen in a particular node, then you do not care about the local one, just look at the normal Reed-Solomon and that will be executed. So, this also has a kind of advantage in efficient recovery mechanism. It's also it's important to remark that ratio between data and parities is increased a little bit, keeping the redundancy to acceptable levels. And they also have a information theoretical result showing that whatever little they add is meets the bound. So, there are some more results you can actually get by reading this, and this has been XOR thing, but we initially actually were comparing our code performance with Sorbos, and so that is why, and this was implemented only in that particular version of the Hadoop, and so we kept on using the same Hadoop for a while. But with the newer Hadoop now, I do not know whether we have any the XOR bus implementation, but there are other better codes that I discuss after the break when we finish our thing. It's called Hitchhiker Code. It's a new framework. We are actually improving the existing RS code into better things. So, this is going to get a flavor of local reconstruction. There are many interesting problems, open problems in actually in achieving the code with this kind of locality, with meeting this locality, and what's the connection between this type of trade-off with the regenerative coding trade-off. What is the connection? There are lots of something that's related, but sometimes it's also very not easy to follow the connections between them. And this also prompted many people, and there are other groups of groups working on local regenerative code within putting this. But they also have to make another remark. The locality in coding itself is an interesting property. So, for example, if you consider Reed-Solomon codes, then you may the part of the Reed-Solomon code, some symbols may have some other unknown properties yet, and there are many theoretical people also working on this area. So, it's a very the rich source of problems, this area, and only some important things have been done now. There are many other open problems there.